So section 11.1 is going to go over parabolas. Parabolas are part of a bigger subject called conic sections. Parabolas have an interesting definition, and I invite you to play around with some of the links that I'll put in the notes to try and understand some of the properties of parabolas. So if we look at one, it's got this interesting point called a focus here. And if I move that around, you notice that it changes the shape of a lot of things. In fact, I can even go underneath that line. Now that line that the parabola opens away from is called the directrix, and this point is called the focus. And there's a good reason for that. There's a lot of applications for parabolas, and one of the slides that I have here will show you one of those applications. That's kind of cool. Now, this is a parabolic shaped radio telescope, and it's kind of indicative of some of the things that you can see when you're looking around for shapes of parabolas, but there's a lot of other things as well. So let's start up here with a better illustration of that. Now, what happens with radio telescopes is that they reflect radio waves to this common point, and that common point is really important. It's called the focus. That's where you'd put the receiver to kind of amplify the signals that you're getting. Other applications of the parabola would include projectile motion. Things tend to fall in a parabolic arc. The Hubble telescope. And the gentleman working on the Hubble telescope here is Andrew Feustel. He's an OCC graduate. When we say you can get anywhere from here, we mean it. Yeah. So check out some of his biography. Sustainable lighting. You can put a parabolic shaped reflector on top of a building and use fiber optic cables to bring in natural sunlight into the interior of a building. Car headlights, searchlights use parabolic shaped reflectors. Parabolic shaped microphone brings you the grunts and groans from Monday Night Football. And my favorite, the Vomit Comet. So the Vomit Comet is a plane that helps you experience weightlessness. It travels at a really steep angle and traces out a parabolic arc near the top, and at the top you'll experience weightlessness. Wow. Now can you see what's interesting and funny about the picture on the bottom left? Yes, somebody brought a cat. That's got to be pretty weird for that cat. In any case, let's work on some more of the properties of the parabola. Now one of the things, one of the things that you could notice is that no matter where you move this around, the vertex, the distance from the vertex to the focus is the same as the vertex to the directrix. And in fact, it's more general than that. Let's click this button here, distance to the focus and directrix. If you play around with this, you'll notice that this distance here from the parabola to the directrix, which is this red line, or from the parabola to the focus is always the same. So I can move this around anywhere I want, and that distance is always going to be the same for any point on the parabola. So that's amazing. Now, that's one of several properties that I want you to be familiar with. One of the other things is that the parabola always opens around the focus and away from the directrix. That's key. You got to keep that orientation correct. Now you can write the formula for a parabola in a couple different ways. Here's the standard form. Here's the vertex form. And now the distance between the vertex and the focus, or the vertex and the directrix, is always the same. It's going to be P. Now I'm not necessarily going to write things as A is here. I might write 4P because A is really going to be related to the distance from the focus to the directrix, the focus to the vertex, and that distance is going to be calculated as A equals 1 over 4P. So let's take a look at another handout that goes with this, and I think it's this one right here. So the distance between the vertex and the focus is P. And you get that by looking at the coefficient of your non-squared term. Now I say non-squared term because you could have a parabola in x squared, which opens up or down depending on the sign here. Or you could have a parabola that opens left and right. Either way, the parabola is always going to be opening around the focus and away from the directrix. So let's see if we can identify a few things for kind of a nice, easy warm-up problem. And let's see. That would be down here. So, for example, A says, label the focus, directrix, and then find the equation. Oh, we also should label the vertex. Now, in this section, the vertex is always going to be at the origin, 0, 0. So we're okay there. That's the vertex. The focus is going to be right here at 3 and 0. And then 1, 2, 3 spaces to the left, that's going to be this vertical line right here. And that vertical line is your directrix. What's the equation at directrix? Well, it's x equal -3. Now that distance between the focus and the vertex right here, or between the vertex and the directrix here, is the same. It's 3. And that's telling me what P has to be. So P equals 3. And that's really enough to help me figure out what the equation of this thing is. Remember, you have a couple different choices for the equation of this parabola. Could be x squared equals 4 times py, but that's only for parabolas that open up and down. For parabolas that open left and right, you're going to have a y squared term. Y squared equals 4px. So in this case, y squared equals 4 times p times x is going to turn out to be y squared equals 4 times p times 3, or excuse me, 4 times 3 times x, or y squared equals 12x. And that's your equation. Nice. You can verify on Desmos that that actually traces out the graph that I suggested here. So let's see. I need to pick up a different link here. So that would be this one. And let's go up to here. Beautiful. There's your graph. Now, let's work one in a more traditional kind of manner. That is, we're going to start out with the equation and see if we can't find the focus and the directrix. So in this case, our equation is x squared equals 8y. Now that coefficient here of y, the coefficient of your non-square term, is going to be 4p. If 4p equals 8, then p equals 2. Now, parabola and x squared is going to open up or down. In this case, since everything is positive, which way does it have to open? It has to open up. So let's take a look at its graph. Put that in right here. Kind of zoom out a little bit. Now, the directrix has to be on the other side of this parabola. Parabola does not cross the directrix. So the directrix is right here at y equals 2, a distance of 2 away from the vertex. 2 away the other direction is going to be right here. That's going to be our focus right there. So got a couple things there for us. That's nice. There's one other thing that we're being asked for here, and that is the focal diameter of the parabola. So what's that? Well, let me help out with that. So going back to let's see, right here, going back to here, focal diameter, actually no, I want to go back to this graph. Let's turn on this little bit right here. So that's a line that extends through the focus from one side of the parabola to the other. And we need to figure out its length. So, okay, well, this is not exactly a square graph anymore. I can square it up that way. This is now a square graph. This distance from this point to the focus is the same as this distance from the focus to the directrix. Now maybe you can calculate that distance. You're going from a y-coordinate of 2 down to a y-coordinate of -2, so nice. That's a total distance of 4. So that this distance here to this distance here also has to be 4, which you can see by looking at the x-coordinates. The focal diameter is really going to be the distance all the way across. Halfway across would be kind of like a focal radius. All the way across is a focal diameter. Now just a kind of quick FYI here. The focal diameter is always going to be 4 times p right here. Focal diameter is always going to be 4 times p. So you don't really need anything fancy to calculate that. Nice. Let's look at another one. X squared equals -4y. Again, find the focus, directrix, focal diameter. So once again, that leading coefficient is going to help us determine what p is. So 4p equals -4. So p equals -1. The vertex is at 0, 0. So let's see if we can't kind of orient a few things here for ourselves. Here's our vertex. We know that this is going to have to open down. There's a negative in this. So you can think of it as p is -1, so you're going to move down. And then you're going to have to find the directrix on the other side of things, here at a distance of 1. Now personally, I don't really worry about the 1 being negative or positive. I just know that it has to be below here, so at the point 0, -1. And then this distance also has to be a distance of 1. So basically I'm just using the absolute value of this. And that would be y equals 1. Oops. Sorry about that. So let's go back here. If we have 4p equals -4, p equals -1, that tells me that the distance between the vertex and the focus is -1. Personally, I just use the fact that that distance is 1. P equals 1 right here. And then this distance also has to be a distance of 1. It's just that it is oriented so that the parabola faces down. Like that. And last but not least, they ask for the focal diameter. So the focal diameter right there, focal diameter is going to be 4 times 1, which is going to be 4. So nice. Let's try a different one. Example D. Example D is going to ask us to find the equation of a parabola with a given vertex. So it's going to be vertex at the origin and the focus is at -7 and 0. So let's give that a shot. Let's shut off example B and turn on what we know from example D. For example D, we've got 0, 0 is our vertex, and -7, 0 is our focus. So let's label these. There we go. Now, that distance between the focus and the vertex is telling us what P has to equal. So in this case, P has to be 7. I guess technically it's -7, but I just know that the distance between these two things is 7. So let me go 7 to the right. And at that point, I'm going to find my directrix, which is right here. And beautiful. So let's see if we can't figure out the equation of the parabola then. So let's see. That's going to be a parabola in y squared. So it's going to be y squared equals 4 times p times x, which is going to mean y squared equals 4 times 7 times x, or y squared equals 28x. But there's something wrong with this. Can you figure out what would be wrong? Well, the thing that's wrong is that this would open to the right. And we know we have to have a parabola that opens to the left. So let's just stick in the negative. I guess technically P is -7, so if you wanted to put in a -7 here, that's fine. I always just do it at the end. It's up to you, whatever works for you. Okay, let's try some more. So we'll go back to Desmos and shut off this stuff. Then, I guess I don't have example E already done for us. Oh well, life goes on. Oh, no, I don't. Find an equation for the parabola that has its vertex at the origin and satisfies the given condition. The directrix is x equal -3. Well, all right, let's do our best on this one. So x equal -3 is going to be here. If we draw ourselves a nice vertical line right there, that kind of indicates a lot about this graph. That distance of P has to be 3. So in particular, I have to have a focus over here at 3 and 0, and a parabola that opens to the right. Now, if it's going to open to the right, then it has to be a parabola in y squared. So it's going to be y squared equals 4 times p times x. And it looks like we're deriving this thing again. This is x equal -3. Y squared equals 4 times 3 times x. So y squared equals 12x. Let's move down to example F. And I might have a little typo in my Desmos stuff about example F, but we'll see if we can't figure this out. So this distance here, well, we don't know that distance here, but we do know the focal diameter. So the diameter is 5/2 plus 5/2, 10/2, which is 5. Now the focal diameter is 5, and that's equal to 4 times p. So we can solve for p from here. 5/4 equals p, and now we're in good shape. So again, let's put that into y squared equals 4 times p times x. So y squared equals 4 times 5/4 times x. The 4's are going to cancel, so we're going to get y squared equals 5x. But something looks wrong. Y squared equals 5x would have to open to the right. So since this one opens to the left, I know it has to be y squared equals -5x. So, yay. And we'll do a couple more here. Example G gives us a directrix at 1/32 for x. That's pretty tight. Let's see if we can't draw that. I'm going to kind of zoom in greatly on this scale. So right here, that's x equal 1/32. Assuming that that's our origin, that tells me that P equals 1/32. Okay. So let's put that into the relevant equation. Now you've got 4 to choose from. So the question is, which is the right one? This one, this one, this one, or this one. Has to be this one. So again, it has to be of the form y squared equals 4px. So y squared equals 4px. That's going to be y squared equals 4 times 1/32 times x. And the astute amongst you might notice and already anticipate the fact that we're going to have to make that a negative. So y squared equals negative 1/8 x. You could, if you really wanted to, you could rearrange this by multiplying by negative 8 and get negative 8y squared equals x. Personally, I don't know, I guess I kind of like this a little bit better, but it doesn't really matter to me one way or another. Can you spot where your focus is going to be? Well, it's going to have to be that same distance to the left, so there'd be negative 1/32 and 0. Yay. Now there's two more that I want to do. At least the first one I'll kind of hint at a little bit because your homework's going to depend on it. And that one's going to be h here. So you've got a parabola that faces to the right. We know what its general form has to be. It has to be a y squared equals 4px. But they don't really give us much. What they tell us is that this square has an area of 36. Well, I know that if this is my vertex and this is my directrix, that distance here has to be p. So I can come up with two different expressions for the area here. One of them is the area is 36, and the other is that the area is p times p, because this is a square. So it's p squared. Now the person that's really on the ball will take plus and minus a square root on both sides and get plus or minus 6 equals p. But realistically, that distance is p. We're going to choose the positive 6 and end up with y squared equals 4 times 6 times x, or 24x. So nice. Last but not least, let's take a look at J. J is stuff that we're going to work on more when we get around to section 11.4. In section 11.4, for all our conic sections, our ellipse, our hyperbola, and our parabola, we're going to start moving them away from the center vertex, or the center at 0, 0, or the vertex at 0, 0, depending on what shape we're working with. In this case, we've got a vertex at negative 3 and 5, and a directrix at 3. So let's kind of draw some stuff to try and orient ourselves a little bit. And let's see. Here. Here. So 1, 2, 3, 4, 5. So at y equal negative 3 and 5, so negative 3 and 5, we've got our vertex. So our parabola is going to open up from there. So somehow or another, like that. And then at y equal 3, down here, we've got our directrix. Now that tells me a very important number. That distance here is p. Now when we move away from the center at 0, 0, or that is the vertex at 0, 0, the general equation for a parabola in x squared is going to look like this. It's going to be x minus h squared equals 4 times p times y minus k. Now that's going to have a vertex at h and k. Well, this is our h and k right there, so we can fill those in. And we also can fill in p, because we know that p has to be this distance. Distance between the vertex and the directrix. So let's see if we can't fill things in. X minus negative 3 equals 4 times p, which is 2, times y minus k. And I'm just going to fill those in a different color. for ease of readability. So it's going to be x minus negative 3 equals 4 times 2 times y minus 5, like that. So overall, it's going to be x plus 3 squared equals 8 times y minus 5. Yay. That's your equation. Now, there's not going to be any problems quite like this in this section, but it is kind of a hint at things to come in section 11.4. So, good luck with these.